Heating an ideal gas inside a fixed rigid container will cause pressure to increase as temperature increases, a phenomenon known as Gay-Lussac's law, as we learned in Lecture 11.1. In Lecture 11.2, we then learned the nature of this built-up pressure. It comes from the gas particles bonding and hence exerting forces upon the container's walls. Now suppose this ideal gas is kept in a container which is able to expand freely. It is sealed, the gas does not leak out, but it is also able to expand or contract freely as shown here. When the container is heated, first the pressure immediately increases because of the increase in the kinetic energy of the gas particles. The particles are getting more agitated, and because of that they will start pounding the wall of the container more vigorously. But because one side of the wall is able to move freely, the gas is able to release this pressure by having a bigger container to accommodate its more energetic state. Hence, the gas is able to maintain its pressure by expanding its volume, which was studied by Jack Charles. At the microscopic level, what happens is that as the particles are pounding on the wall of the container, they exert force onto the wall. The impact drives the wall bit by bit. Of course, the impact from one gas particle hardly makes any difference, but we are typically talking about moles of gas particles here. That is one followed by 23 or 24 zeros of particles pounding on the walls. And this results in noticeable effect. The container is expanding. Let's say the gas drives the wall of the container by delta L as it expands. We can compute the amount of work that the gas has done to expand itself at constant pressure. So please take note this important assumption, namely that pressure is kept constant, which underlies the subsequent derivation. As defined in the beginning of Lecture 6, work done is defined as force times displacement. In this context, the force is the one exerted by the gas particle when it hits the wall. The displacement is delta L. Delta L, however, is the expanded volume of the container divided by the area of the wall. In turn, force over area gives us pressure. Hence, the work done by the expanding gas is given by pressure times the change in volume of the container. Notice that this equation is also reversible. The volume of the container may contract instead of expanding, in which case work will be negative, meaning that work is done on the gas instead of by the gas. That is to say, an external agent will have to compress the gas. Our lecture, however, does not stop here because immediately you should notice one problem in this derivation. What happens if the gas expands or contracts without maintaining its pressure? Expansion at constant pressure is just one of the thermodynamics processes governed by Charles' law. Boyle's law, for instance, governs another type of expansion whereby temperature is kept constant, yet the gas is also expanding. It is also doing work on the container's wall. However, this derivation is no longer valid because this derivation assumes constant pressure during expansion, which is clearly not the case in Robert Boyle's study. Hence, the question is, how do we compute the work done by expanding gas or varying pressure? Well, fortunately, it is not a totally new question for us. We solved similar question before when we going through Lecture 6. How do we compute work done by varying force? Well, you see, once again, I would like to emphasize the microscopic origin of pressure in this context. It comes from the average forces that the gas particles deliver on the wall upon impact. Hence, varying pressure is akin to varying these average forces. Thereby, the question of finding work done by the gas or varying pressure is akin to the question of finding work done by varying force. We know how to do this. We learned it before. We drew the plot of force versus displacement, and we sliced this plot into tiny displacement steps, whereby we assume that for each step the force is constant, so that we can use the usual equation F times displacement to compute the fractional amount of work which results from these tiny displacement steps. The total work done is simply the scalar sums of these fractions. We are not going to do exactly the same in this case of expanding gas, but instead of plotting force versus displacement, we are plotting pressure versus volume in this case. In short form, this diagram is known as PV diagram. P stands for pressure, which constitutes the vertical axis, and V stands for volume, which constitutes the horizontal axis. In this diagram, any thermodynamic process, such as gas expanding at constant temperature, can be plotted. The arrow indicates the direction from its initial pressure and volume state to its final pressure and volume state. As seen here, pressure is not constant. But we are going to slice this plot into small increments of delta V and assume pressure to be constant at each increment. Then we can compute the work done during each increment given as such, in accordance to what we just derived in the last slide. The subscript phi indicates that the pressure at certain point along that plot depends on the volume at that particular point. It is not constant, but it's not purely arbitrary either. It is a function of volume. The total work done by the gas expanding from state 1 to state 2 is thus given by the summation of these fractions of work done over a small increment delta phi. The smaller this increment is, the more fractions are involved, but the more accurate the result is going to be. So theoretically, we should take the limit of delta phi to 0 and sum all the infinite numbers of terms that result. This is essentially a process called integration in calculus. So this is one of those very few moments in this course whereby we have to resort to calculus in order to expand our repertoire of equations to solve more generic problems. You will understand what I mean when studying the next chapter. Lastly, unlike the change in internal energy, which only depends on the change in final and initial temperature, work done by the gas is dependent on which path is taken. The easiest way to see this is by recalling that integrating a function is akin to computing the area under the plot of that function. So in this particular illustration, this integration computes this shaded area. But going from state 1 to state 2, the gas does not necessarily have to follow this blue line. It could go in accordance to the green line, for example. Of course, such process may not be categorized into any of the basic thermodynamic processes we have learned so far, perhaps a combination of them. But in any case, there are many paths for the gas to reach the final state 2 from the initial state 1, and each path gives different shaded area in the PhET diagram. That means the work done is also different. In this illustration, it is clear that the gas does more work going to state 2 from state 1 by following the green line than it does by following the blue line. Work done is thus dependent on the process that happens in between the final and the initial state of the gas.